learning objectives. In this chapter, the user will learn the following in detail: issues regarding classification and prediction, different classification methods including decision tree induction, Bayesian classification, neural network technology, nearest neighbor classifier, case-based reasoning, fuzzy set theory, genetic algorithm, prediction, linear and multiple regression, nonlinear regression, other regression models, classifier accuracy. Introduction. Classification is a form of data analysis that extracts models describing important data classes. Such models, called classifiers, predict categorical, discrete, unordered class labels. For example, we can build a classification model to categorize bank loan applications as either safe or risky. Such analysis can help provide us with a better understanding of the data at large. Many classification methods have been proposed by researchers in machine learning, pattern recognition, and statistics. Most algorithms are memory resilient, typically assuming a small data size. Recent data mining research has built on such work, developing scalable classification and prediction techniques capable of handling large amounts of disk-resident data. Classification has numerous applications, including fraud detection, target marketing, performance prediction, manufacturing, and medical diagnosis. Bayesian classification. Bayes classification methods. Bayesian classifiers are statistical classifiers. They can predict class membership probabilities, such as the probability that a given tuple belongs to a particular class. Bayesian classifiers have also exhibited high accuracy and speed when applied to large databases. Naive Bayesian classifiers assume that the effect of an attribute value on a given class is independent of the values of the other attributes. This assumption is called class conditional independence. It is made to simplify the computations involved, and in this sense, it is considered naive. Bayes' theorem. Let X be a data tuple. In Bayesian terms, X is considered evidence. As usual, it is described by measurements made on a set of n attributes. Let H be some hypothesis such that the data tuple X belongs to a specified class C. For classification problems, we want to determine P of H given X, the probability that the hypothesis H holds given the evidence or observed data tuple X. Probability of H given X is the posterior probability or a posteriori probability of H conditioned on X. In contrast, P of H is the prior probability or a priori probability of H. P of X is the prior probability of X. Bayes' theorem is useful in that it provides a way of calculating the posterior probability P of H given X from P of H, Px given H, and Px. Bayes' theorem is P of H given X equals P of X given H into P of H divided by P of X. Naive Bayesian classification. The naive Bayesian classifier or simple Bayesian classifier works as follows. Let D be a training set of tuples and their associated class labels. As usual, each tuple is represented by an n-dimensional attribute vector X equals x1, x2 going up to xn, depicting n measurements made on the tuple from n attributes, respectively a1, a2 up to an. Suppose that there are m classes C1, C2 going up to Cm. Given a tuple X, the classifier will predict that X belongs to the class having the highest posterior probability, conditioned on X. That is, the naive Bayesian classifier predicts that tuple X belongs to the class Ci if and only if probability of Ci given X is greater than probability of Cj given X, for j lying between 1 and m, and j not equal to I. Thus we maximize probability of Ci given X. The class Ci for which probability of Ci given X is maximized is called the maximum posteriori hypothesis. By Bayes' theorem, P of Ci given X equals P of X given Ci into P of Ci divided by P of X. As Px is constant for all classes, only P of X given Ci into P of Ci needs to be maximized. If the class prior probabilities are not known, then it is commonly assumed that the classes are equally likely. That is, P of C1 equals P of C2, going on up to P of Cm, and we would therefore maximize P of x given Ci. Otherwise, we maximize P of x given Ci into P of Ci. Note that the class prior probabilities may be estimated by P of Ci equals to mod of Ci, d divided by mod of d, where mod of Ci, d is the number of training tuples of class Ci in D. Given data sets with many attributes, it would be extremely computationally expensive to compute P of x given Ci. To reduce computation in evaluating P of x given Ci, the naive assumption of class conditional independence is made. This presumes that the attributes' value are conditionally independent of one another, given the class label of the tuple. That is, that there are no dependence relationships among the attributes. Thus, P of x given Ci is equal to product k equals 1 to n probability of xk given Ci equal to P of x1 by Ci into P of x2 by Ci and so on up to P of xn by Ci. To compute P of x given Ci, we consider the following. If ak is categorical, then P of xk given Ci is the number of tuples of class Ci in D, having the value of xk for ak, divided by mod of Ci, d, the number of tuples of class Ci in D. If ak is continuous valued, then we need to do a little bit more work, but the calculation is pretty straightforward. A continuous valued attribute is typically assumed to have a Gaussian distribution with mean mu and standard deviation sigma, defined by g of x, mu and sigma equals 1 by square root of 2 pi sigma into e to the power of minus x minus mu whole square divided by 2 sigma squared, so that P of xk given Ci equals g of xk, mu Ci and sigma Ci. To predict the class label of x, P of x given Ci, P of Ci is evaluated for each class of Ci. The classifier predicts that the class label of tuple x is a class Ci if and only if P of x given Ci into P of Ci is greater than P of x given Cj, P of Cj, for j lying between 1 and m, and j not equal to I. Case-based reasoning. Case-based reasoning, CBR, classifiers use a database of problem solutions to solve new problems. Business applications of CBR include problem resolution for customer service help desks, where cases describe product-related diagnostic problems. When given a new case to classify, a case-based reasoner will first check if an identical training case exists. If one is found, then the accompanying solution to that case is returned. If no identical case is found, then the case-based reasoner will search for training cases having components that are similar to those of the new case. Conceptually, these training cases may be considered as neighbors of the new case. If cases are represented as graphs, this involves searching for subgraphs that are similar to subgraphs within the new case. The case-based reasoner tries to combine the solutions of the neighboring training cases to propose a solution for the new case. If incompatibilities arise with the individual solutions, then backtracking to search for other solutions may be necessary. The case-based reasoner may employ background knowledge and problem-solving strategies to propose a feasible combined solution. Challenges in case-based reasoning. Finding a good similarity metric and suitable methods for combining solutions. The selection of salient features for indexing training cases. The development of efficient indexing techniques. The system's efficiency suffers as the time required to search for and process relevant cases increases. Cases that are redundant or that have not proved useful may be discarded for the sake of improved performance. These decisions, however, are not clear-cut and their automation remains an active area of research. Classifier accuracy. Classifier's accuracy prediction. Classifier accuracy prediction is part of meta-learning, and there are several techniques proposed for such a system. These meta features are very useful properties that can be used as input variables for a regression model. In this approach, a regression model is used as a meta-learning model for the meta-learning system. To predict the classifier's accuracy using meta features and regression, the following steps should be employed. Choose one or more meta features on which the prediction should be based. Extract these meta features from the training datasets. Evaluate the classifier on all the training datasets, computing its accuracy. Train the regression model on these datasets by using the meta features along with the computed accuracies as input variables for the regression analysis. Giving the meta features of any new problem to the constructed regression model, the model will return the predicted accuracy of the classifier. This figure shows a schematic view of meta-learning. On the left, the case base is created. On the right, an unknown dataset is processed and a suitable classifier is recommended. Classifier accuracy measures. Accuracy of a classifier M, ACK-M, percentage of test set tuples that are correctly classified by the model M. Error rate, misclassification rate of M equals 1 minus accuracy of M. Given M classes, CM I, J, an entry in a confusion matrix indicates number of tuples in class I that are labeled by the classifier as class J of F. Alternative accuracy measures, for example, for cancer diagnosis. Sensitivity equals T positive by positive, true positive recognition rate. Specificity, T negative by negative, true negative recognition rate. Precision, T positive by T positive plus F positive. Accuracy, sensitivity into pos over positive plus specificity into negative into positive plus negative. This model can also be used for cost-benefit analysis. Evaluating the accuracy of a classifier or predictor. Hold-out method. Given data is randomly partitioned into two independent sets. Training set, example 2 of 3 for model construction. Test set, for example 1 by 3 for accuracy estimation. Random sampling, a variation of holdout. Repeat holdout k times, accuracy equals average of the accuracies obtained, F. Cross-validation, k-fold, where k equals 10 is most popular. Randomly partition the data into k mutually exclusive subsets, each approximately of equal size. At ith iteration, use di as test set and others as training set. Leave one out, k-folds where k equals number of tuples for small-sized data. Stratified cross-validation. Folds are stratified so that class distance in each fold is approximately the same as that in the initial data. Bootstrap. This works well with small datasets. Samples the given training tuples uniformly with replacement. That is, each time a tuple is selected, it is equally likely to be selected again and re-added to the training set F. Several bootstrap methods, and a common one is 0.632 bootstrap. Suppose we are given a dataset of D tuples. The dataset is sampled D times with replacement, resulting in a training set of D samples. The data tuples that did not make it into the training set end up forming the test set. About 63.2% of the original data will end up in the bootstrap, and the remaining 30.8% will form the test set. Since 1 minus 1 by D into D is approximately equal to E minus 1, that is 0.368. Repeat the sampling procedure k times overall accuracy of the model. Accuracy of M equals summation of I equals 1 to k 0.632 into accuracy of MI test set plus 0.368 into accuracy of MI train set. Decision tree induction. Decision tree induction is the learning of decision trees from class-labeled training tuples. A decision tree is a flow chart-like tree structure where each internal node, non-leaf node, denotes a test on an attribute, each branch represents an outcome of the test, and each leaf node or terminal node holds a class label. The topmost node in a tree is the root node. A decision tree for the concept buys computer, indicating whether an all-electronics customer is likely to purchase a computer. Each internal non-leaf node represents a test on an attribute. Each leaf node represents a class, either buys computer, yes, or buys computer, no. How are decision trees used for classification? Given a tuple X for which the associated class label is unknown, the attribute values of the tuple are tested against a decision tree. A path is traced from the root to the leaf node, which holds a class prediction for that tuple. Decision trees can easily be converted to classification rules. Why are decision tree classifiers so popular? The construction of decision tree classifiers does not require any domain knowledge or a parameter setting, and therefore is appropriate for exploratory knowledge discovery. Decision trees can handle multi-dimensional data. Their representation of acquired knowledge in tree form is intuitive and generally easy to assimilate by humans. The learning and classification steps of decision tree induction are simple and fast. In general, decision tree classifiers have good accuracy. However, successful use may depend on the data at hand. Decision tree induction algorithms have been used for classification in many application areas such as medicine, manufacturing and production, financial analysis, astronomy, and molecular biology. Decision trees are the basis of several commercial rule induction systems. ID3, Iterative Dichotomizer, and CART, Classification and Regression Trees, were invented independently of one another at around the same time, yet follow a similar approach for learning decision trees from training tuples. ID3, C4.5, and CART adopt a greedy, that is, non-backtracking approach in which decision trees are constructed in a top-down recursive divide and conquer manner. Most algorithms for decision tree induction also follow a top-down approach, which starts with a training set of tuples and their associated class labels. The training set is recursively partitioned into smaller subsets as the tree is being built. The strategy is as follows. The algorithm is called with three parameters, D, attribute list, and attribute selection method. We refer to D as a data partition. Initially, it is the complete set of training tuples and their associated class labels. The parameter attribute list is a list of attributes describing the tuples. Attribute selection method specifies a heuristic procedure for selecting the attribute that best discriminates the given tuples according to class. This procedure employs an attribute selection measure such as information gain or the Gini index. Whether the tree is strictly binary is generally driven by the attribute selection measure. Some attribute selection measures, such as the Gini index, enforce a resulting tree to be binary. Others, like information gain, do not, therein allowing multi-way splits, that is, two or more branches to be grown from a node. The tree starts as a single node n, representing the training tuples in D. Algorithm: generate a decision tree. Generate a decision tree from the training tuples of data partition D. Input: data partition D, which is the set of training tuples and their associated class labels. Attribute list, the set of candidate attributes. Attribute selection method, a procedure to determine the splitting criterion that best partitions the data tuples into individual classes. This criterion consists of a splitting attribute and possibly either a split point or splitting subset. Output: a decision tree. Method: Step 1. Create a node n. Step 2. If tuples in D are all of the same class C, then return n as a leaf node labeled with the class C. Step 3. If attribute list is empty, then return n as a leaf node labeled with the majority in class D, majority voting. Step 4. Apply attribute selection method D attribute list to find the best criterion. Step 5. Label node n. Step 6. If splitting attribute is discrete valued and multi-way splits allowed, then not restricted to binary trees. Step 7. Attribute list splitting attribute. Remove splitting attribute. Step 8. For each outcome of J splitting criterion, partition the tuples and grow subtrees for each partition. Step 9. Let Dj be the set of data tuples in D satisfying outcome J. A partition. Step 10. If Dj is empty, then. Step 11. Attach a leaf labeled with the majority class in D to node n. Step 12. Else attach the node returned by generic decision tree Dj attribute list to node n. End. Step 13. Return n. If the tuples in D are all of the same class, then node n becomes a leaf and is labeled with that class. Steps 2 and 3. Note that steps 4 and 5 are terminating conditions. All terminating conditions are explained at the end of the algorithm. Otherwise, the algorithm calls attribute selection method to determine the splitting criterion. The splitting criterion tells us which attribute to test at node n by determining the best way to separate or partition the tuples in D into individual classes. The splitting criterion also tells us which branches to grow from node n with respect to the outcomes of the chosen test. More specifically, the splitting criterion indicates the splitting attribute and may also indicate either a split point or a splitting subset. The splitting criterion is determined so that, ideally, the resulting partitions at each branch are as pure as possible. A partition is pure if all the tuples in it belong to the same class. In other words, if we split up the tuples in D according to the mutually exclusive outcomes of the splitting criterion, we hope for the resulting partitions to be as pure as possible. The node n is labeled with the splitting criterion, which serves as a test at the node. Step 7. A branch is grown from node n for each of the outcomes of the splitting criterion. The tuples in D are partitioned accordingly. Step 10 to 11. This figure shows 3 possibilities for partitioning tuples based on the splitting criterion, each with examples. Let A be the splitting attribute. If A is discrete valued, then one branch is grown for each known value of A. If A is continuous valued, then 2 branches are grown corresponding to A less or equal to split point and A greater than split point. If A is discrete valued and a binary tree must be produced, then the test is of the form A belongs to SA, where SA is the splitting subset for A. A is discrete valued. In this case, the outcomes of the test at node n correspond directly to the known values of A. A branch is created for each known value AJ of A and labeled with that value. Partition DJ is a subset of class-labeled tuples in D having value AJ of A. Because all the tuples in a given partition have the same value for A need not be considered in any future partitioning of the tuples. Therefore, it is removed from attribute list. A is continuous valued. In this case, the test at node n has 2 possible outcomes corresponding to the conditions A is less or equal to split point and greater than split point, respectively, where each split point is a split point returned by attribute selection method as part of the splitting criterion. In practice, the split point A is often taken as a midpoint of 2 known adjacent values of A and therefore may not actually be a pre-existing value of A from the training data. The 2 branches are grown from N and labeled according to the previous outcomes. The tuples are partitioned such that D1 holds a subset of class-labeled tuples in D, for which A less than or equal to split point, while D2 holds the rest. A is discrete valued, and a binary tree must be produced, as dictated by the attribute selection measure or algorithm being used. The test at node n is of the form A belong to SA, where SA is a splitting subset for A, returned by attribute selection method as part of the splitting criterion. It is a subset of the known values of A. If a given tuple has values AJ of A, and if AJ belongs to SA, then the test at node N is satisfied. The two branches are grown from N. By convention, the left branch out of N is labeled S, so that D1 corresponds to the subset of class labeled tuples in D that satisfy the test. The right branch out of N is labeled No, so that D2 corresponds to the subset of class labeled tuples from D that do not satisfy the test. The algorithm uses the same process recursively to form a decision tree for the tuples at each resulting partition Dj of D. The recursive partitioning stops only when any of the following terminating conditions is true. All the tuples in partition D represented at node N belong to the same class. There are no remaining attributes on which the tuples may be further partitioned. In this case, majority voting is employed. This involves converting node N into a leaf and labeling it with the most common class in D. Alternatively, the class distribution of the node tuples may be stored. There are no tuples for a given branch, that is, a partition Dj is empty. In this case, a leaf is created with the majority class in D. The resulting decision tree is returned. Attribute selection measures. An attribute selection measure is a heuristic for selecting the splitting criterion that best separates a given data partition D of class-labeled training tuples into individual classes. If we were to split D into smaller partitions according to the outcomes of the splitting criterion, ideally each partition would be pure, that is, all the tuples that fall into a given partition would belong to the same class. Attribute selection measures are also known as splitting rules because they determine how the tuples at a given node are to be split. The attribute selection measures provide a ranking for each attribute describing the given training tuples. The attribute having the best score for the measure is chosen as a splitting attribute for the given tuples. If the splitting attribute is continuous valued, or if we are restricted to binary trees, then, respectively, either a split point or a splitting subset must also be determined as part of the splitting criterion. The tree node created for partition D is labeled with the splitting criterion. Branches are grown for each outcome of the criterion, and the tuples are partitioned accordingly. Three popular attribute selection measures: information gain, gain ratio, Gini index. Information gain. ID3 uses information gain as its attribute selection measure. Let node N represent or hold the tuples of partition D. The attribute with the highest information gain is chosen as a splitting attribute for node N. This attribute minimizes the information needed to classify the tuples in the resulting partitions and reflects the least randomness or impurity in these partitions. Such an approach minimizes the expected number of tests needed to classify a given tuple and guarantees that a simple but not necessarily the simplest tree is found. The expected information needed to classify a tuple in D is given by info D equals minus summation of I equal to 1 to m pi log 2 pi, where pi is the non-zero probability that an attribute tuple in D belongs to class Ci and is estimated by mod of Ci, D by mod D. A log function to the base 2 is used because the information is encoded in bits. Info D is just the average amount of information needed to identify the class label of a tuple in D. Info D is also known as the entropy of D. Now, suppose we were to partition the tuples in D on some attribute A having V distinct values, A1, A2 going up to AV, as observed from the training data. If A is discrete valued, these values correspond directly to the V outcomes of a test on A. Attribute A can be used to split D into V partitions or subsets, D1, D2 going on up to DV, where Dj contains those tuples in D that have outcomes of Aj of A. These partitions would correspond to the branches grown from node N. How much more information would we still need after the partitioning to arrive at an exact classification? This amount is measured by info A of D equals to summation of j equals 1 to v mod of dj divided by mod of d into info dj. The term mod of dj or mod of d acts as the weight of the jth partition. Info A of d is the expected information required to classify a tuple from D based on the partitioning by A. The smaller the expected information still required, the greater the purity of the partitions. Information gain is defined as the difference between the original information requirement, that is, based on just the proportion of classes, and the new requirement, that is, obtained after partitioning on A. That is, gain A equals info D minus info A D. The attribute A with the highest information gain, gain A, is chosen as a splitting attribute at node n. Gain ratio. The information gain measure is biased towards tests with many outcomes. That is, it prefers to select attributes having a large number of values. For example, consider an attribute that acts as a unique identifier, such as product ID. A split on product ID would result in a large number of partitions, as many as there are values, each one containing just one tuple. Because each partition is pure, the information required to classify dataset D based on this partitioning would be info product ID of D equals 0. Therefore, the information gained by partitioning on this attribute is maximal. Clearly, such a partitioning is useless for classification. C4.5. A successor of ID3 uses an extension to information gain known as gain ratio, which attempts to overcome this bias. It applies a kind of normalization to information gain using a split information value defined analogously with info D as split info A D equals minus summation of j equals 1 to v mod dj divided by mod d into log 2 of mod dj divided by mod d. This value represents the potential information generated by splitting the training data set D into V partitions corresponding to the V outcomes of test on attribute A. Note that for each outcome, it considers the number of tuples having that outcome with respect to the total number of tuples in D. It differs from information gain, which measures the information with respect to classification that is acquired based on the same partitioning. The gain ratio is defined as gain ratio A equals gain of A divided by split info A of D. Gini index. The Gini index is used in CART, C-A-R-T. Using the notation previously described, the Gini index measures the impurity of D, a data partition or set of training tuples, as Gini D equals 1 minus summation of I equals 1 to m pi squared, where pi is the probability that a tuple in D belongs to class Ci and is estimated by mod of Ci, D divided by mod of D. The sum is computed over m classes. The Gini index considers a binary split for each attribute. Let's first consider the case where A is a discrete valued attribute having V distinct values, A1, A2 and so on up to AV, occurring in D. To determine the best binary split on A, we examine all the possible subsets that can be formed using known values of A. Each subset SA can be considered as a binary test for attribute A of the form A belongs to SA. Given a tuple, this test is satisfied if the value of A for the tuple is among the values listed in SA. If A has V possible values, then there are 2 V possible subsets. For example, if income has 3 possible values, namely low, medium, high, then the possible subsets are low, medium, high, low, medium, low, high, medium, high, low, medium, high, and empty. We exclude the power set low, medium, high, and the empty set from consideration since, conceptually, they do not represent a split. Therefore, there are 2V minus 2 possible ways to form 2 partitions of the data D based on a binary split on A. When considering a binary split, we compute a weighted sum of the impurity of each result partition. For example, if a binary split on A partitions D into D1 and D2, the Gini index of D given that partitioning is Gini A of D equals mod of D1 by D into Gini D1 plus mod of D2 by D into Gini D2. For each attribute, each of the possible binary splits is considered. For a discrete valued attribute, the subset that gives the minimum Gini index for that attribute is selected as its splitting subset. For continuous valued attributes, each possible split point must be considered. The strategy is similar to that described earlier for information gain, where the midpoint between each pair of sorted adjacent values is taken as a possible split point. The point giving the minimum Gini index for a given continuous valued attribute is taken as a split point of that attribute. Recall that for a possible split point of A, D1 is a set of tuples in D satisfying A less or equal to split point, and D2 is a set of tuples in D satisfying A greater than split point. The reduction in impurity that would be incurred by a binary split on a discrete or continuous valued attribute A is delta Gini A equals Gini D minus Gini A D. The attribute that maximizes the reduction in impurity, or equivalently, has the minimum Gini index, is selected as a splitting attribute. This attribute and either its splitting subset for a discrete valued splitting attribute or split point for a continuous valued splitting attribute together form the splitting criterion. Other attribute selection measures. Chi-D, a decision tree algorithm that is popular in marketing, uses an attribute selection measure that is based on the statistical chi-square test for independence. Other measures include C-SEP, which performs better than information gain and the Gini index in certain cases, and G-statistic, an information theoretic measure that is close approximation to chi-square distribution. Attribute selection measures based on the minimum description length MDL principle have the least bias towards multi-valued attribute. MDL-based measures use encoding techniques to define the best decision tree as the one that requires the fewest number of bits to both encode the tree and encode the exceptions to the tree, that is, cases that are not correctly classified by the tree. Its main idea is that the simplest of solutions is preferred. Other attribute selection measures consider multivariate splits. The CART system, for example, can find multivariate splits based on a linear combination of attributes. Multivariate splits are a form of attribute or feature construction where new attributes are created based on the existing ones. Tree pruning. When a decision tree is built, many of the branches will reflect anomalies in the training data due to noise or outliers. Tree pruning methods address this problem of overfitting the data. Such methods typically use statistical measures to remove the least reliable branches. Pruned trees tend to be smaller and less complex and thus easier to comprehend. They are usually faster and better at correctly classifying independent test data, that is, of previously unseen tuples, than unpruned trees. There are two common approaches to tree pruning: pre-pruning and post-pruning. In the pre-pruning approach, a tree is pruned by halting its construction early. Upon halting, the node becomes a leaf. The leaf may hold the most frequent class among the subset tuples or the probability distribution of those tuples. When constructing a tree, measures such as statistical significance, information gain, Gini index, and so on can be used to assess the goodness of a split. If partitioning the tuples at a node would result in a split that falls below a pre-specified threshold, then further partitioning of the subset halted. There are difficulties, however, in choosing an appropriate threshold. High thresholds could result in oversimplified trees, whereas low thresholds could result in very little simplification. The post-pruning removes subtrees from fully grown trees. A subtree at a given node is pruned by removing its branches and replacing it with a leaf. The leaf is labeled with the most frequent class among the subtree being replaced. The cost complexity pruning algorithm used in CART is an example of the post-pruning approach. This approach considers the cost complexity of a tree to be a function of the number of leaves in the tree and the error rate of the tree. It starts from the bottom of the tree. For each internal node n, it computes the cost complexity of the subtree at n and the cost complexity of the subtree at n if it were to be pruned, that is, replaced by a leaf node. The two values are compared. If pruning the subtree at node n would result in a smaller cost complexity, then the subtree is pruned, otherwise it is kept. A pruning set of class-labeled tuples is used to estimate cost complexity. This set is independent of the training set used to build the unpruned tree and of any test set used for accuracy estimation. The algorithm generates a set of progressively pruned trees. In general, the smallest decision tree that minimizes the cost complexity is preferred. A method called pessimistic pruning is used, which is similar to the cost complexity method in that it also uses error rate estimates to make decisions regarding subtree pruning. Pessimistic pruning uses the training set to estimate error rates. The pessimistic pruning method adjusts the error rates obtained from the training set by adding a penalty so as to counter the bias incurred. Figure shows an unpruned decision tree and a pruned version of it. Figure shows an example of subtree repetition, where an attribute is repeatedly tested along a given branch of the tree, and subtree replication, where duplicate subtrees exist within a tree. Scalability and decision tree induction. The efficiency of existing decision tree algorithms such as ID3, C4.5, and CART has been well established for relatively small datasets. Efficiency becomes an issue of concern when these algorithms are applied to the mining of very large real-world databases. The pioneering decision tree algorithms that we have discussed so far have the restriction that the training tuples should reside in memory. More scalable approaches capable of handling training data that are too large to fit in memory are required. Earlier strategies to save space including discretizing continuous valued attributes and sampling data at each node. Rainforest adapts to the amount of main memory available and applies to any decision tree induction algorithm. The method maintains an AVC set where AVC stands for attribute, value, class label for each attribute at each tree node, describing the training tuples at the node. The AVC set of an attribute A at node n gives the class label counts for each value of A for the tuples at n. The set of all AVC sets at a node n is the AVC group of n. The size of an AVC set for attribute A at node n depends only on the number of distinct values of A and the number of classes in the set of tuples at n. Typically, this size should fit in memory even for real-world data. Rainforest also has techniques, however, for handling the case where the AVC group does not fit in memory. Therefore, the method has high scalability for decision tree induction in very large datasets. BOAT, Bootstrapped Optimistic Algorithm for Tree Construction, is a decision tree algorithm that takes a completely different approach to scalability. It is not based on the use of any special data structures. Instead, it uses a statistical technique known as bootstrapping to create several smaller samples or subsets of the given training data, each of which fits in memory. Each subset is used to construct a tree, resulting in several trees. The trees are examined and used to construct a new tree, T0, that turns out to be very close to the tree that would have been generated if all the original training data had fit in memory. BOAT can use any attribute selection measure that selects binary split, and that is based on the notion of purity of partitions such as the Gini index. BOAT uses a lower bound on the attribute selection measure to detect if this very good tree, T0, is different from the real tree, T, that would have been generated using all of the data. It refines T0 to arrive at T. BOAT usually requires only 2 scans of D. BOAT was found to be 2 or 3 times faster than Rainforest while constructing exactly the same tree. An additional advantage of BOAT is that it can be used for incremental updates. BOAT can take new insertions and deletions for the training data and update the decision tree to reflect these changes without having to reconstruct the tree from scratch. The figure shows the use of data structures to hold aggregate information regarding the training data. For example, these AVC sets describe the given data. This is one approach to improving the scalability of decision tree induction. Visual mining for decision tree induction. Perception-based classification, PBC, is an interactive approach based on multidimensional visualization techniques and allows the user to incorporate background knowledge about the data when building a decision tree. The resulting trees tend to be smaller than those built using traditional decision tree induction methods and so are easier to interpret while achieving about the same accuracy. PBC uses a pixel-oriented approach to view multidimensional data with its class label information. The circle segments approach is adapted, which maps D-dimensional data objects to a circle that is partitioned into D segments, each representing one attribute. Here, an attribute value of data object is mapped to one colored pixel reflecting the object's class label. This mapping is done for each attribute value pair of each data object. Sorting is done for each attribute to determine the arrangement order within a segment. The PBC system displays a split screen consisting of a data interaction window and a knowledge interaction window. The data interaction window displays the circle segments of the data under examination, while knowledge interaction window displays the decision tree constructed so far. Initially, the complete training set is visualized in data interaction window, while the knowledge interaction window displays an empty decision tree. A tree is interactively constructed as follows. The user visualizes the multidimensional data in the data interaction window and selects a splitting attribute and one or more split points. The current decision tree in the knowledge interaction window is expanded. The user selects a node of the decision tree. The user may either assign a class label to the node, which makes the node a leaf, or request the visualization of the training data corresponding to the node. This leads to a new visualization of every attribute except the ones used for splitting criteria on the same path from the root. The interactive process continues until a class has been assigned to each leaf of the decision tree. The trees constructed with PBC were compared with trees generated by CART, C4.5 and Sprint algorithms from various datasets. The trees created with PBC were of comparable accuracy with the tree from the algorithmic approaches, yet were significantly smaller and thus easier to understand. The figure shows a screenshot of PBC, a system for interactive decision tree construction. Multi-dimensional training data are viewed as circle segments in the data interaction window, left. The knowledge interaction window, right, displays the current decision tree. Fuzzy set theory. Fuzzy set approaches. Rule-based systems for classification have the disadvantage that they involve sharp cutoffs for continuous attributes. For example, consider the following rule for customer credit application approval. The rule essentially says that applications for customers who have had a job for 2 or more years and who have a high income, that is, of at least $50,000, are approved. If years employed is greater or equal to 2 and income is greater or equal to $50,000, then credit is approved. By this rule, a customer who has had a job for at least 2 years will receive a credit if her income is, say, $50,000, but not if it is $49,000. Such harsh thresholding may seem unfair. Instead, we can discretize income into categories and then apply fuzzy logic to allow fuzzy thresholds or boundaries to be defined for each category. Rather than having a precise cutoff between categories, fuzzy logic uses truth values between 0.0 and 1.0 to represent the degree of membership that a certain value has in a given category. Each category then represents a fuzzy set. Hence, with fuzzy logic, we can capture the notion that an income of $49,000 is more or less high, although not as high as an income of $50,000. Fuzzy logic systems typically provide graphical tools to assist users in converting attribute values to fuzzy truth values. Fuzzy set theory is useful for data mining systems performing rule-based classification. It provides operations for combining fuzzy measurements. Suppose that in addition to the fuzzy set for income, we define the fuzzy sets junior employee and senior employee for the attribute years employed. Suppose also that we have a rule that say test high income and senior employee in the rule antecedent if part for a given employee X. If these two fuzzy measures are ANDed together, the minimum of their measure is taken as a measure of the rule. In other words, M high income and senior employee into X equals min of M high income into X, M senior employee into X. Intuitively, this is like saying that a rope is as strong as its strongest strand. Given a tuple to classify, more than one fuzzy rule may apply. Each applicable rule contributes a vote for membership in the categories. Typically, the truth values for each predicted category are summed and these sums are combined. Several procedures exist for translating the resulting fuzzy output into a defuzzified or crisp value that is returned by the system. Fuzzy logic systems have been used in numerous areas for classification, including market research, finance, healthcare, and environmental engineering. Genetic algorithms. Genetic algorithms attempt to incorporate ideas of natural evolution. An initial population is created consisting of randomly generated rules. Each rule can be represented by a string of bits. As a simple example, suppose that samples in a given training set are described by two Boolean attributes A1 and A2, and that there are two classes C1 and C2. The rule, if A1 and not A2, then C2, can be encoded as the bit string 100, where the two leftmost bits represent attributes A1 and A2, respectively, and the rightmost bit represents the class. Similarly, the rule if not A1 and not A2, then C1 can be encoded as 001. If an attribute has k values, where k is greater than 2, then k bits may be used to encode the attribute's values. Classes can be encoded in a similar fashion. Based on the notion of survival of the fittest, a new population is formed to consist of the fittest rules in the current population, as well as offspring of these rules. Typically, the fitness of a rule is assessed by its classification accuracy on a set of training samples. Offspring are created by applying genetic operators such as crossover and mutation. In crossover, substrings from pairs of rules are swapped to form new pairs of rules. In mutation, randomly selected bits in a rule string are inverted. The process of generating new populations based on prior populations of rules continues until a population P evolves where each rule in P satisfies a pre-specified fitness threshold. Genetic algorithms are easily parallelizable and have been used for classification as well as other optimization problems. In data mining, they may be used to evaluate the fitness of other algorithms. Issues regarding classification and prediction. A bank loans officer needs analysis of her data to learn which loan applicants are safe and which are risky for the bank. A marketing manager at All Electronics needs data analysis to help guess whether a customer with a given profile will buy a new computer. A medical researcher wants to analyze breast cancer data to predict which one of 3 specific treatments a patient should receive. The data analysis task is classification, where a model or classifier is constructed to predict class, categorical labels such as safe or risky for the loan application data, yes or no for the marketing data, or treatment A, treatment B, or treatment C for the medical data. These categories can be represented by discrete values where the ordering among values has no meaning. For example, the values 1, 2, and 3 may be used to represent treatments A, B, and C, where there is no ordering implied among this group of treatment regimes. Suppose that the marketing manager wants to predict how much a given customer will spend during a sale at All Electronics. This data analysis task is an example of numeric prediction, where the model constructed predicts a continuous valued function or ordered value as opposed to a class label. This model is predictor. Regression analysis is a statistical methodology that is most often used for numeric prediction. Hence, the two terms tend to be used synonymously, although other methods for numeric prediction exist. Classification and numeric prediction are the two major types of prediction problems. General approach to classification. Data classification is a two-step process consisting of a learning step where a classification model is constructed and a classification step where the model is used to predict class labels for given data. A classifier is built describing a predetermined set of data classes or concepts. This is the learning step or training phase where a classification algorithm builds a classifier by analyzing or learning from a training set made up of database tuples and their associated class labels. Since the class label of each training tuple is provided, this step is also known as supervised learning. That is, the learning of the classifier is supervised in that it is told to which class each training tuple belongs. It contrasts with unsupervised learning or clustering, in which the class label of each training tuple is not known and the number or set of classes to be learned may not be known in advance. This first step of the classification process can also be viewed as the learning of a mapping function, y equals f of x, that can predict the associated class label y of a given tuple x. In the second step, the model is used for classification. First, the predictive accuracy of the classifier is estimated. If we were to use the training set to measure the classifier's accuracy, this estimate would likely be optimistic because the classifier tends to overfit the data. Therefore, a test set is used, made up of test tuples and their associated class labels. They are independent of the training tuples, meaning that they were not used to construct the classifier. The accuracy of a classifier on a given test set is a percentage of test set tuples that are correctly classified by the classifier. The associated class label of each test tuple is compared with the learning classifier's class prediction for that tuple. The figure shows the data classification process, learning, and classification. Neural network technology. A neural network is a set of connected input-output units in which each connection has a weight associated with it. Neural network learning is also referred to as connectionist learning due to the connections between units. Neural networks involve long training times and are therefore more suitable for applications where this is feasible. They require a number of parameters that are typically best determined empirically, such as the network topology or structure. Neural networks have been criticized for their poor interpretability. Neural network algorithms are inherently parallel. Parallelization techniques can be used to speed up the computation process. The most popular neural network algorithm is backpropagation. Advantages of neural networks: high tolerance of noisy data, ability to classify patterns on which they have not been trained, can be used when little knowledge of the relationships between attributes and classes is available, suited for continuous valued inputs and outputs, unlike most decision tree algorithms. A multilayer feed-forward neural network. A multilayer feed-forward neural network consists of an input layer, one or more hidden layers, and an output layer. Each layer is made up of units. The inputs are fed into the input layer and are then weighted and fed simultaneously to a second layer of neuron-like units known as a hidden layer. The outputs of the hidden layer units can be input to another hidden layer and so on. The number of hidden layers is arbitrary, although in practice, usually only one is used. The weighted outputs of the last hidden layer are input to units making up the output layer, which emits the network's prediction for given tuples. The units in the input layer are called input units. The units in the hidden layers and the output layer are sometimes referred to as neurodes due to their symbolic biological basis or as output units. A network containing two hidden layers is called a three-layer neural network. It is a feed-forward network since none of the weights cycles back to an input unit or to a previous layer's output unit. It is fully connected in that each unit provides input to each unit in the next forward layer. Each output unit takes as input a weighted sum of the outputs from units in the previous layer. It applies a nonlinear activation function to the weighted input. Multilayer feed-forward neural networks are able to model the class prediction as a nonlinear combination of the inputs. From a statistical point of view, they perform nonlinear regression. Multilayer feed-forward networks, given enough hidden units and enough training samples, can closely approximate any function. Figure shows a multi-layer feed-forward neural network. Defining a network topology. The number of units in the input layer, the number of hidden layers, if more than one, the number of units in each hidden layer, and the number of units in the output layer in the network topology should be decided. Normalizing the input values for each attribute measured in the training tuples will help speed up the learning phase. Typically, input values are normalized so as to fall between 0 and 1.0. Discrete valued attributes may be encoded such that there is one input unit per domain value. Neural networks can be used for both classification, to predict the class label of a given tuple, and numeric prediction, to predict a continuous valued output. For classification, one output unit may be used to represent two classes. If there are more than two classes, then one output unit per class is used. Network design is a trial and error process and may affect the accuracy of the resulting trained network. The initial values of the weights may also affect the resulting accuracy. Once a network has been trained and its accuracy is not considered acceptable, it is common to repeat the training process with a different network topology or a different set of initial weights. Cross-validation techniques for accuracy estimation can be used to help decide when an acceptable network has been found. A number of automated techniques have been proposed that search for a good network structure. These typically use a hill climbing approach that starts with an initial structure that is selectively modified. Backpropagation. Backpropagation learns by iteratively processing a data set of training tuples, comparing the network's prediction for each tuple with the actual known target value. The target value may be the known class label of the training tuple for classification problems or a continuous value for numeric prediction. For each training tuple, the weights are modified so as to minimize the mean squared error between the network's prediction and the actual target value. These modifications are made in the backwards direction, that is, from the output layer through each hidden layer down to the first hidden layer, hence the name backpropagation. Although it is not guaranteed, in general the weights will eventually converge and the learning process stops. Algorithm backpropagation. Neural network learning for classification or numeric prediction using the backpropagation algorithm. Input D. A dataset consisting of the training tuples and their associated target values. L. The learning rate. Network, a multilayer feed-forward network. Output, a trained neural network. The method will be as seen on the screen. Initialize the weights. The weights in the network are initialized to small random numbers, for example, ranging from -1 to 1 or -0.5 to 0.5. Each training tuple X is processed by the following steps. Propagate the inputs forward. First, the training tuple is fed to the network's input layer. The inputs pass through the input units unchanged. That is, for an input unit J, its output OJ is equal to its input value IJ. The net input to a unit in the hidden or output layers is computed as a linear combination of its inputs. Each such unit has a number of inputs to it that are in fact the outputs of the units connected to it in the previous layers. Each connection has a weight. To compute the net input to the unit, each input connected to the unit is multiplied by its corresponding weight, and this is summed. Given a unit j in a hidden or output layer, the net input ij to unit j is ij equals summation of I, wij big OI plus theta j, where wij is the weight of the connection unit from unit I in the previous layer to unit j, big OI is the output of unit I from the previous layer, and theta j is the bias of the unit. Each unit in the hidden and output layers takes its net input and then applies an activation function to it. The function symbolizes the activation of the neuron represented by the unit. The logistic or sigmoid function is used. Given the net input ij to unit j, then oj, the output of unit j, is computed as big Oj equals 1 by 1 plus e to the power minus I j. This function is also referred to as a squashing function because it maps a large input domain onto the smaller range of 0 to 1. The logistic function is nonlinear and differentiable, allowing the backpropagation algorithm to model classification problems that are linearly inseparable. We compute the output values Oj for each hidden layer up to and including the output layer, which gives a network's prediction. Figure shows the hidden or output layer unit j. The inputs to unit j are outputs from the previous layer. These are multiplied by the corresponding weights to form a weighted sum, which is added to the bias associated with unit j. A nonlinear activation function is applied to the net input. For ease of explanation, the inputs to unit j are labeled y1, y2 going up to yn. If unit j were in the first hidden layer, then these inputs would correspond to the input tuple x1, x2 going up to xn. Backpropagate the error. The error is propagated backward by updating the weights and biases to reflect the error of the network's prediction. For a unit j in the output layer, the error rj is computed by rj equals oj into 1 minus oj into tj minus oj, where oj is the actual output of unit j and tj is the known target value of the given training tuple, and oj, 1 minus oj, is a derivative of the logistic function. To compute the error of a hidden layer unit j, the weighted sum of the errors of the units connected to unit j in the next layer are considered. The error of a hidden layer unit j is rj equals oj into 1 minus oj sum of k rk wjk, where wjk is the weight of the connection from unit j to a unit k in the next higher layer, and rk is the error of unit k. The weights and the biases are updated to reflect the propagated errors. Weights are updated by the following equations, where delta wij is a change in weight wij. Delta wij equals L into rj into oi. Wij equals wij plus delta wij. Biases are updated by the following equations, where delta theta j is a change in bias theta j. Delta theta j equals L into rj. Theta j equals theta j plus delta theta j. Note that here we are updating the weights and biases after the presentation of each tuple. This is referred to as case updating. Alternatively, the weight and bias increments could be accumulated in variables so that the weights and biases are updated after all the tuples in the training set have been presented. This latter strategy is called epoch updating, where one iteration through one training set is an epoch. The mathematical derivation of backpropagation employs epoch updating. Yet in practice, case updating is more common because it tends to yield more accurate results. Terminating condition. Training stops when all delta wij in the previous epoch are so small as to be below some specified threshold, or the percentage of tuples misclassified in the previous epoch is below some threshold, or a pre-specified number of epochs has expired. The figure shows an example of multi-layer feed-forward neural network. Inside the black box, backpropagation and interpretability. A major disadvantage of neural networks lies in their knowledge representation. Acquired knowledge in the form of a network of units connected by weighted links is difficult for humans to interpret. This factor has motivated research in extracting the knowledge embedded in training neural networks and in representing that knowledge symbolically. Methods include extracting rules from networks and sensitivity analysis. Various algorithms for rule extraction have been proposed. The methods typically impose restrictions regarding procedures used in training the given neural network, the network topology, and the discretization of input values. Fully connected networks are difficult to articulate. Hence, often the first step in extracting the rules from neural networks is network pruning. This consists of simplifying the network structure by removing weighted links that have the least effect on the trained network. Rules are derived relating combinations of activation values with corresponding output unit values. Similarly, the sets of input values and activation values are studied to derive rules describing the relationship between the input layer and the hidden layer units. Finally, the two sets of rules may be combined to form if-then rules. Other algorithms may derive rules of other forms, including M of n rules, decision trees with M of n tests, fuzzy rules, and finite automata. Sensitivity analysis is used to assess the impact that a given input variable has on a network output. The input to the variable is varied, while the remaining input variables are fixed at some value. Meanwhile, changes in the network output are monitored. The knowledge gained from this analysis form can be represented in rules such as if x decreases 5%, then y increases 8%. This figure shows the rules can be extracted from training neural networks. Nonlinear regression. Some nonlinear models can be modeled by a polynomial function. A polynomial regression model can be transformed into linear regression model. For example, y equals w0 plus w1 x1 plus w2 x2 plus w3 x3, convertible to linear with new variables x2 equals x2, x3 equals x3. Y equals w0 plus w1 x1 plus w2 x2 plus w3 x3 f. Other functions such as a power function can also be transformed to linear model f. Some models are intractable nonlinear. For example, sum of exponential terms. Possible to obtain least square estimates through extensive calculation on more complex formulae. Wherever you are along the line on the linear plot shown on screen, moving 1 unit to the right will move you up 5 units. The 1/5 ratio is constant, so the relationship is linear. In this figure, moving a unit to the right on the line above will carry you up a different amount depending on where you are, that is, nonlinear. If x predicts y, then they have a nonlinear relationship if the effect on y of a small change in x depends on the current value of x. Note that if you have more than one predictor, nonlinearity can occur as 2 or more predictors combine. For example, putting the price up by 1p will cause you to sell 1,000 fewer newspapers when there is a political story on the front cover, but only 500 fewer with sports on the cover. Other regression models. Other regression-based models. Generalized linear model. Foundation on which linear regression can be applied to modeling categorical response variables. Variance of y is a function of the mean value of y, not a constant. Logistic regression models the probability of some event occurring as a linear function of a set of predictor variables. Poisson regression models the data that exhibit a Poisson distribution f. Log linear models for categorical data. Approximate discrete multidimensional probability distributions. Also useful for data compression and smoothing f. Regression trees and model trees. Trees to predict continuous values rather than class labels. Regression trees and model trees. Regression tree proposed on CART system. CART, classification and regression trees. Each leaf stores a continuous valued prediction. It is the average value of the predicted attribute for the training tuples that reach the leaf F. Model tree, proposed by Quinlan in 1992. Each leaf holds a regression model, a multivariate linear equation for the predicted attribute, a more general case than regression tree F. Regression and model trees tend to be more accurate than linear regression when the data are not represented well by a simple linear model. Prediction. Linear and multiple regression. Prediction. Predicting the identity of one thing based purely on the description of another related thing. Not necessarily future events, just unknowns. Based on the relationship between a thing that you can know and a thing you need to predict. Numerical prediction is similar to classification. Construct a model. Use model to predict continuous or ordered value for a given input F. Prediction is different from classification. Classification refers to predict categorical class label. Prediction models continuous valued functions F. Major method for prediction, regression. Model the relationship between one or more independent or predictor variables and a dependent or response variable F. Regression analysis. Linear and multiple regression. Nonlinear regression. Other regression methods: generalized linear model, Poisson regression, log linear models, regression trees. Linear regression. Linear regression involves a response variable y and a single predictor variable x. Y equals W0 plus W1x, where W0 y-intercept and W1 slope are regression coefficients f. Method of least squares estimates the best fitting straight line f. W1 equals sum of I equals 1 to mod d xi minus x bar into yi minus y bar over summation of I equals 1 to mod d xi minus x bar whole squared. W0 equals y bar minus W1 x bar. Multiple linear regression involves more than one predictor variable. Training data is of the form x1, y1, x2, y2 going up to x modulus d, y modulus d. Example, for 2D data we may have y equals W0 plus W1 x1 plus W2 x2. Solvable by extension of least square method or using SAS S+. Many nonlinear functions can be transformed into the above. K nearest neighbor classifiers. Nearest neighbor classifiers are based on learning by analogy, that is by comparing a given test tuple with training tuples that are similar to it. The training tuples are described by n attributes. Each tuple represents a point in an n-dimensional space. In this way, all the training tuples are stored in an n-dimensional pattern space. When given an unknown tuple, a k nearest neighbor classifier searches the pattern space for the k training tuples that are closest to the unknown tuple. These k training tuples are the k nearest neighbors of the unknown tuple. Closeness is defined in terms of distance metric such as Euclidean distance. The Euclidean distance between 2 points or tuples, say x1, equals x11, x12, and so on up to x1n, and x2 equals x21, x22, and so on up to x2n. Is distance x1, x2 equals square root of sum of I equals 1 to n x1i minus x2i whole squared. For each numeric attribute, we take the difference between the corresponding values of that attribute in tuple x1 and in tuple x2, square this difference and accumulate it. The square root is taken of the total accumulated distance count. Typically, we normalize the values of each attribute before using the equation. This helps prevent attributes with initially large ranges, for example income, from outweighing attributes with initially smaller ranges, for example binary attributes. Min-max normalization, for example, can be used to transform a value v of a numeric attribute a to v dash in the range 0, 1 by computing v dash equals v minus min a divided by max a minus min a, where min a and max a are the minimum and maximum values of attribute a. For k nearest neighbor classification, the unknown tuple is assigned to the most common class among its k nearest neighbors. When k equals 1, the unknown tuple is assigned the class of the training tuple that is closest to it in pattern space. Nearest neighbor classifiers can also be used for numeric prediction, that is, to return a real valued prediction for a given unknown tuple. In this case, the classifier returns the average value of the real valued labels associated with the k nearest neighbors of the unknown tuple. But how can distance be computed for attributes that are not numeric but nominal or categorical, such as color? For nominal attributes, a simple method is to compare the corresponding value of the attribute in tuple x1 with that in tuple x2. If the two are identical, example, tuples x1 and x2 both have the color blue, then the difference between the two is taken as 0. If the two are different, for example, tuple x1 is blue but tuple x2 is red, then the difference is considered to be 1. What about missing values? If the value of a given attribute A is missing in tuple x1 and or in tuple x2, we assume the maximum possible difference. Suppose that each of the attributes has been mapped to the range 0, 1. For nominal attributes, we take the difference values to be 1 if either one or both the corresponding values of A are missing. If A is numeric and missing from both tuples x1 and x2, then the difference is also taken to be 1. If only one value is missing and the other, which we will call v dash, is present and normalized, then we can take the difference to be either 1 minus v dash or 0 minus v dash, that is, 1 minus v dash or v dash, whichever is greater. Nearest neighbor classifiers use distance-based comparisons that intrinsically assign equal weight to each attribute. The method, however, has been modified to incorporate attribute weighting and pruning of noisy data tuples. The choice of a distance metric can be critical. The Manhattan distance or other distance measurements may also be used. Nearest neighbor classifiers can be extremely slow when classifying test tuples. If D is a training database of mod D tuples and k equals 1, then O into mod of D comparisons are required to classify a given test tuple. By pre-sorting and arranging the stored tuples into search trees, the number of comparisons can be reduced to O into log of mod D. Parallel implementation can reduce the running time to a constant, that is 0, 1, which is independent of mod D. Other techniques to speed up classification time include the use of partial distance calculations and editing the stored tuples. In the partial distance method, we compute the distance based on a subset of the n attributes. If this distance exceeds a threshold, then further computation for the given stored tuple is halted, and the process moves on to the next stored tuple. The editing method removes training tuples that prove useless. This method is also referred to as pruning or condensing because it reduces the total number of tuples stored. Conclusion. In this chapter, we have covered the following in detail: issues regarding classification and prediction, different classification methods including decision tree induction, Bayesian classification, neural network technology, K, nearest neighbor classifier, case-based reasoning, fuzzy set theory, genetic algorithm, prediction, linear and multiple regression, nonlinear regression, other regression models, classifier accuracy.